Hi, my name is Sarah Zuderman and the date is July 25th of 2021, and today we will be going over the Unit 2 case connection studies. So the first case that I chose was case 2, and this follows a 16-year-old female who was recently diagnosed with a deficiency of muscle glycogen phosphorylase. She and her family are concerned and ask the following questions. For the first question, she asks, I am not sure I understand the issue. Can you explain how muscle glycogen is used normally during exercise? To start from the beginning, when you eat food, this gets broken down into micronutrients, which can be used for energy or stored for later use. Glycogen is a form of energy storage in your cells. Glycogen can be stored primarily in your muscles and in your liver. When you have not eaten for a while, your body enters what we call the fasted state. In the fasted state, your muscles will use an enzyme to break down glycogen for energy. And to describe what an enzyme is, it is used to regulate the timing of reactions and alter molecules involved in reactions. So in this case, an enzyme called glycogen phosphorylase will release an intermediate, which is then mutated into glucose 6-phosphate, and glucose 6-phosphate is ultimately broken down into energy and pyruvate. And for explanation of what pyruvate is a molecule that is involved in a process called oxidative phosphorylation, which is just a pathway that creates lots of energy, otherwise known as ATP, for use in the muscle. And her second question was, I really like to take long walks. Will I still be able to do this with my friends? As a reply, I'd stated that she has been diagnosed with McArdle's disease. This is a rare disease that influences skeletal muscle glycogen breakdown. The most common symptom of McArdle's disease is exercise intolerance. Exercise intolerance manifests as early tiredness with exercise, muscle stiffness with exercise, and muscle pain. Another symptom of exercise intolerance is prolonged tightening of the muscles, tendons, and nearby tissues classified as contractures. High-intensity exercise can cause severe pain leading to muscle damage, and this would be termed rhabdomyolysis, or muscle breakdown, which can then instigate a complication in your kidneys due to the waste products released in your bloodstream accumulating and damaging the tissue. However, regular mild to moderate exercise with sufficient energy sources, such as the ingestion of simple carbohydrates before you exercise, has proven to result in improved patient outcomes compared with their inactive counterparts. So that's someone who would sit on the couch all day just because getting up would hurt them to walk around. I would suggest that you take shorter walks and remember to take breaks when you feel pain and tiredness in your muscles. In her third question, she asks, as a result of this deficiency, will I need to get up at night to eat and maintain my blood glucose level? I stated this is unnecessary to wake up throughout the night in order to maintain blood glucose level. Although, to ensure that you have ample blood glucose levels throughout the day, some diet modifications may need to occur. Adopting a diet with increased portions of complex carbohydrates found in vegetables, fruits, cereals, pasta, and rice to about 65% of your diet has proven to alleviate symptoms of McArdle's disease. Another diet adaptation suggested is the lowering of portions of fat in your diet to about 20%. And her last question was, do I need to worry about producing excessive lactate during intense anaerobic exercise? So as we talked about previously, glycogen is broken down into glucose intermediates by glycogen phosphorylase. Since you are lacking this enzyme, this conversion is unable to occur. Therefore, lactate increases in exercise cannot be due to glycogen breakdown. Although patients with McArdle's disease do have similar increases in lactate release during exercise as we would see in a normal healthy individual, suggesting that lactate formation is mandatory for optimal energy production of contracting muscle. So, for in the next case, I chose case 3, which follows a 5-year-old boy who was brought into the pediatrician office for his annual visit. The mother reports that he has been a sickly infant and often appears drowsy. She also has concerns over her son's persistent thirst and frequent urination. Blood samples are taken for insulin measurement at time 0 and 1 after a glucose loading test. The results of this test are illustrated in the table below. So the patient's blood sample has a much lower insulin level than what we would see in the control, and then 1 after hour the glucose load, you would normally see insulin levels increase as you see in this control, and our patient has decreased insulin production. So what is this information likely to suggest about the underlying biochemical basis for the patient's symptoms? And I said that this is hyperglycemia that we are seeing due to low insulin production. Insulin is typically released to utilize the glucose ingested through either oxidation or storage for later use. Although, as stated earlier, the young boy is experiencing insufficient insulin release, leaving the glucose in his bloodstream unoxidized. The patient is experiencing drowsiness and possible polyphagia due to his body's inept use of this glucose in his system and subsequent decrease in cellular ATP. Hyperglycemia is known to raise the osmotic pressure within the bloodstream, pulling intracellular fluid out of the tissues in the cells, causing cellular dehydration and subsequently persistent thirst. The excessive fluid within the bloodstream must be excreted, leading to polydipsia, otherwise known as frequent urination. Lastly, hyperglycemia can weaken a patient's immune system, corresponding with the mother's description of the boy as a sickly infant. So, another question that they asked was, what would you predict the patient's fasted blood glucose levels to be given his current condition? Above normal range, within the normal range, or below the normal range? So I would predict the patient's fasted blood glucose levels to be above the normal range. This is due to the decreased insulin production that does not allow the glucose to be taken out of the bloodstream for use in energy production, storage in the form of glycogen, or the conversion of glucose into triacylglycerol, which can be stored in adipose tissue. Based on this diagnosis, what 2 regulatory enzymes are likely to be active in this individual's current condition? As we have learned in class, glucose is the primary source of energy throughout the body. As previously mentioned, due to decreased insulin levels, the body is unable to utilize the glucose that is consumed within his diet. With this in mind, the body must utilize an alternative pathway to obtain energy sources, such as lipolysis. A major regulatory enzyme of lipolysis or fat breakdown is hormone-sensitive lipase, which is located on the endothelial cells to hydrolyze triacylglycerol, which was stored in fat, into free fatty acids to be used for energy. And this is to compensate for the energy that we can't use from the glucose that is sitting in the bloodstream. Lastly, in a healthy individual, insulin secretion will typically inhibit glucagon secretion. These 2 regulatory hormones work in opposite ways. So it makes sense that insulin will typically inhibit this glucagon secretion. Although in patients with diabetes who are unable to make endogenous insulin, which is insulin that is secreted by the pancreas, will instead experience a pathological process. So the administration of exogenous insulin, which is insulin that is manufactured and given to someone subcutaneously, is ineffective for the use of suppression of glucagon secretion. So this is saying that the insulin that you give them is not actually suppressing glucagon, resulting in the elevated hepatic glucose production or gluconeogenesis. So gluconeogenesis is happens in the liver, and it has 4 unique regulatory enzymes, including pyruvate carboxylase, which can carboxylate pyruvate into oxaloacetate. And this oxaloacetate is moved out of the mitochondria, and the phosphoenolpyruvate carboxykinase then convert oxaloacetate into phosphoenolpyruvate. And fructose 1,6-bisphosphatase is another enzyme used, which converts fructose 1,6-bisphosphate into fructose 6-phosphate. And lastly, glucose 6-phosphatase, which dephosphorylates glucose 6-phosphate into free glucose, which can then be released from the liver and into the bloodstream, therefore increasing the hyperglycemia within the child. And that is all, and thank you for listening, and have a great day.